So hey, I'm Maciej, and I'm very thankful for all of you to came here. And I will talk about serverless and machine learning. And foremost, I need to apologize. I was sick last week, and I have a bit of sore throat, but I hope I will be able to speak for the next 40-50 minutes. So let's start with getting to know each other a little bit. I will start, then everyone will say who they are, for what they are doing, and yeah, turning on devices usually helps for them to work. Okay, so I'm Maciej. I'm a developer building serverless solutions on AWS. I work for Merapar. And Merapar is a software house that builds solutions for media companies. So I had opportunity to work for Sky UK, that I guess everyone here knows quite good. Hayu, if you are following Kardashians, then you probably know it as well. And other companies like Liberty, Latin America, and so on. And at this point, I can tell you that all of those companies and more are doing serverless solutions, and they are doing serverless solutions that are like client-facing. For Sky has like dozens, like 16, 17 million clients or something like that, regularly, daily using their services, and they have some serverless solutions that are client-facing and handle all that traffic. So it's not like serverless is just good for small, cheap solutions. Apart from that, I'm a community builder in AWS, and I blog and tweet about mostly serverless. And now it's your turn. Firstly, if you could raise hand if you are doing serverless. Okay, that makes sense. Why you came here? Since you are on DevOps, are you doing serverless with Java? Okay, I actually don't. Okay, so half of those who does serverless. Yeah, that makes sense. Probably Java is not the first language that you choose if you are doing serverless. Okay, and is there anyone who identifies themselves as a data scientist? None. Okay, that's actually good, because I neither. I'm a developer, but I had opportunity to work in the cross-functional teams with data scientists. So we together built some solutions on AWS. And during this talk, I will explore two main ways of building serverless machine learning solutions on AWS, because I'm doing things on AWS, so that's like my area. First will be purpose-built AI services that we can use that AWS offers us. So that's probably cheating if you are saying you are doing machine learning and serverless, and you are just using ready AI services. But that's quite good cheating. We usually don't want to do a lot of things ourselves. We just want to build stuff that work. But sometimes those purpose-built AI services are not enough for our use cases, and that's why when we need to build models ourselves, and we will explore if we can actually achieve this with serverless. But first, let's get on the same page. What is serverless and why are we using it? So probably if you hear serverless, the first thing that comes to mind is AWS Lambda. This is the serverless service. Basically, very low setup. You just put your code, you attach some triggers, some events that will invoke it. It may be the HTTP request from your API that Lambda will consume and produce the result, or event from the queue, or change in the database, whatever. But it turns out that serverless is not just Lambda. Quite the opposite. Lambda is just a part of the serverless solutions, because AWS in this case offers much more serverless solutions. So you have DynamoDB, the NoSQL database. You have, like I said before, queues, SQS. You have step functions to orchestrate processes. You have Glue for ETL. You even have the serverless versions of regular services. So you have Aurora SQL Serverless, which is SQL database that is offered as a serverless. So what makes things serverless and why we use those services? Basically, there is one goal of serverless services, and that's simplifying operations, and that's basically the root of all things. Because serverless offers us high-level building blocks, just like Lego bricks. And by the way, Lego is well known in the serverless community for building serverless solutions and being expert at that. I don't think that's I think that's like pretty significant. Serverless services offer things that just work. You don't have to set up networking. You don't have to set up auto-scaling. You just put your code in the Lambda function, and you don't worry about it too much, that if more users will start using your service, the Lambda will not handle it, because AWS, without your involvement in this, will automatically create more Lambda runtimes that will handle the increased traffic. You also don't set up anything to achieve high availability, because in the case that, I don't know, the machine, the server where your function currently was invoked will blow up, or the availability zone in AWS will blow up, Meteor will strike it, whatever, you will not even notice it, because AWS will automatically move your workload to a different availability zone. So you get those things, maybe not for free, but without configuring them, without having to do much to achieve those wonderful things. And like I said, you don't configure a lot, and even if you configure things with serverless services, it's on slightly different level than we used to, because we with serverless more often configure what we want to have than how we want it to be done, so we can achieve it. Let me tell you what I mean by this. Let's take DynamoDB, the NoSQL database. You can set the write and read throughput that you want to have, and that's basically it. Under the hood, AWS will take care of distributing your whole database across number of partitions that will be needed to give you the expected read and write throughput. And that's basically the opposite of what you would do if you would set up the similar type of database yourself. You would set up the database on the number of partitions, and that would give you the throughput that it can handle. So that's the opposite. Like, we are setting high-level parameters, and AWS under the hood takes care of how to achieve this. Or you don't set anything with DynamoDB, for example, and it just scales up and down automatically on demand. So this simplification, what it gives us, or the purpose for it, is basically to reduce costs. And you can find a lot of arguments over internet if serverless is too cheap, or quite the opposite, if the costs are too high. And basically that's not what really matters with serverless, if single invocation of some Lambda function costs too much, because what matters is the total cost of ownership. So not only how much it costs to run it on production, but also how much it costs to deliver it to production. And if you don't have to set up networking, auto-scaling, high availability, you don't have to think about all those things, and you don't have to spend weeks of development teams building this stuff and achieving this auto-scaling, achieving this high availability. Basically, that's money that is saved. And in addition to this, you can deliver things to production much, much faster. So that's like win-win from the business perspective. Of course, if you look at correct numbers. So the question, I guess, is, can you apply those features to machine learning solutions to also be able to deliver things to production faster? Well, let's see. So first approach that I mentioned is basically cheating. It's not doing machine learning models ourselves, but using something that is already gave to us by AWS. So AWS has a bunch of AI services. Those are not all that are available. That is just few that looked nice on the slide, I guess. We have all the funny names from AWS that you probably have to check few times before you learn what exactly what is exactly the service under the name, because you have services like recognition, comprehend, personalize, and so on. And just like serverless services, those are high-level building blocks that you can just take and put into your architecture and just start using them. And in most cases, you, just like with Lambda functions and all other serverless services, you don't really have to set up everything or anything with them. You're just using them. And that's not the only like serverless similarity, because they often follow the pay-per-use billing. So you are paying for number of requests that you make, so there are no upfront costs and so on. So basically, like, that's not exactly serverless services. There are more like SaaS, like software as a service services, but they fit very, very nicely into the serverless landscape, I would say. And what can those services do for you? Well, they serve like all the generic stuff that you may encounter and may need from machine learning services. So you can use textract to extract text from images, so the OCR. You have the Amazon Comprehend that does natural language processing to extract information from the text. You have Amazon Lookout for metrics that you can feed with metric, and well, it will detect your anomalies for you if something goes different than usually in your metrics. You can use Personalize to generate recommendations. So if you have e-commerce store, you want to show to users, okay, users who bought this frequently bought also this, and this. Or you have VOD service, and who doesn't have the VOD service those days? And you want to have the rail viewers like you also like those shows. So this is the Amazon Personalize for you. But not only those general purpose capabilities are offered, there are also some, I would say, quite specific capabilities. So, for example, with the comprehend, you can parse invoices. So it will know that, okay, so we are looking at the invoice, so it will try to extract all the typical invoice elements. You can parse medical documents, which is like completely different thing apparently from parsing normal text, because like there are very specific names there to look, and but there is no standard of those documents. So you have Amazon Comprehend Medical that will take care of this for you, extract the valuable information like about the illnesses and drugs, and give you the standardized codes for them. And you have Amazon Recognition that offers you detecting personal protective equipment, so the helmets and gloves and so on that are required on some facilities and so on. So you can probably find for most of your use cases that you can encounter that AWS already created a service that will do what you need. So why using this? Well, because our job is not really to build machine learning models, even if you are data scientists. Our job is to deliver solutions, and that's, I think, more appealing to us, like to developers. So instead of building something on your own and spending months and months on perfecting the machine learning model just for your use case, you can rely on AWS or any provider, Google and so on. They offer similar capabilities to solve your business problems without reinventing the wheel, because probably AWS did it a little bit better. Maybe it will be a few % worse for your specific use case, but if you can use it today instead in 2-3 months that will take your data scientist team to build it, probably that's still better. But probably the biggest advantage is easier productionization of such solutions. I don't know if you work a lot on machine learning solutions, but what I found and the other people that I spoke with also confirmed that there's a huge gap between the machine learning model that data scientists will do and having this working on the production. Because something working in Jupyter Notebook, which is great and which can be shown to stakeholders on the demo, and stakeholders will say, yes, great, that's our good results. We have AI, great. Let's see it tomorrow working on our website in our service. No, that's next 3 months that will take us to take what we have in this Jupyter Notebook to actual production. Oh, that's bollocks. Okay. Here, if we already have something working in the cloud, the whole architecture can be as simple as this, to be honest. Let's say we have Amazon recognition and we want to generate some labels for the, some tags for the images that user uploads. So that's pretty basic use case, probably. User uploads the photo, that triggers Lambda function. Lambda function triggers, makes call to the Amazon recognition. Hey, this is photo. Tell me what's on this photo. Okay, here are your results. You can save it to DynamoDB or wherever. And we don't have to train model for this. We don't have to deploy our model. We don't have to set up anything. That's a call that you can make straight ahead to recognition. Yeah, so that's as simple as this. You just say detect labels, and it will give you labels and where on the image are those things. But to be honest, not all AWS services, AI services, are just as simple as that. I mentioned before the Amazon Personalize, and I mentioned that before because that's service that I probably worked most with. And that's service that can give you content recommendations. So basically you feed it with the interactions, you feed it with items, and then you can ask for recommendations for the user. So that's unfortunately not so simple as recognition, because first you have to train your model. So that's pre-trained model that you have to train for your specific data sets. But still, you can do this probably much easier than if you would try to deploy your own model altogether. Because what you need to do is basically to create training data sets. So basically take your real interactions, real items from the last few months, let's say. You put them into S3, then you go to Amazon Personalize, say, okay, here are the data sets, train me the model. You wait 2 hours, and then you have Personalize ready to be used, generating recommendations for your specific content, knowing your users' behaviors. And of course, that's not the end, because then you, for your users, generate recommendations, but you also have a feedback loop of sending back the new interactions. And of course, new content catalog, because the content catalog always changes. You have new items in your store, you have new VOD items in your VOD service, and so on. So that's take a moment to train, but that's something that you basically click in AWS, and the training happens 2 hours later. You can attach your Lambda to it and just start using it. And there are few things that you get as a bonus, I would say, by using AI services from AWS. First of them is that they are continuously improved. Probably if you would do the model yourself, you would do this once, or your data scientists would do this once. And probably business wouldn't justify keeping the, I don't know, 5 people data science team continuously improving the model by 0.1% every month or whatever. That's probably not justified in the most cases. But AWS can justify it because it's used not by one client, but by thousands of clients. So you can observe over time, and that's actually true, that those models are getting better and better. And you have metrics to confirm it. So that's nice. Other nice things with those services and the life hack how to improve the latency of those services, especially in case of those services where you have your model trained, is just put them on the production. This is the chart of request versus latency. So we have request on green and latency in blue. So you can see when we are when day starts and more and more users use our service, latency drops basically 2 times. So that's pretty nice. Not to start, the latency wasn't bad at all in the first place, because latency of 80 milliseconds for the recommendations is not a bad thing. Okay, but let's say you look over dozen of AWS AI services and you didn't find what you needed. So what you do? Well, you have to create your model yourself, or take some existing model from the internet, train you on your data, and deploy it. So can we do this with serverless? Let's see. First of all, what we not be talking about is Amazon SageMaker. If you are somewhat familiar with AWS, you know that SageMaker is the go-to place for the machine learning, for building machine learning models, training them, deploying, and so on. And it's supposed to simplify all those operations, those ML ops, to actually deliver model on the production. That's probably true. I'm saying probably because I tried to get into the SageMaker a few times, and it just scares me. If you go there, you see SageMaker having 24 or more capabilities that it can do, so you basically don't know where to start. And there is the SageMaker serverless inference, which is probably nice, although it has all the problems of the regular Lambda functions that we'll see how to use in a moment, because it under the hood uses the Lambda function. So maybe it's not exactly worth the added complexity to the architecture, to the deployment process, to the development, because then you have to use the SageMaker library. I think we can do just as well with just pure Lambda functions. Okay. When we discuss machine learning solutions, I would like to split them in two versions, or two possible types of solutions. One would be synchronous, where it's client-facing. So basically, you have your Lambda function or whatever service, and user asks you for something, and you are doing machine learning inference and returning the results. That's, for example, how recommendations work, right? User enters the page, and you generate at this moment generate recommendations for them. And in those solutions, we require low latency, because obviously user won't wait 3 seconds for you to load the recommendations. But also we have the other type, the asynchronous inference, where basically the machine learning happens in the background process. So that was, for example, the example with the Amazon recognition, where a new image was uploaded to S3 bucket. Then we ask recognition to detect what's on the page, what's on the image, and generate the labels. And in this process, few seconds of latency is not really a big issue, especially if those few seconds of latency will happen only from time to time, and usually our latency will be lower. So I would say the second one type is much easier to do, but we can also handle the first one. Okay, so generally the idea would be to have Lambda function with Python runtime. Sorry, but Python is the go-to language for machine learning, with some machine learning library in it, transformers, PyTorch, whatever. Basically, that's where my knowledge of machine learning ends. And a trained model, yeah, because we need some model trained. So we put everything nicely in this Lambda function, and it's ready to serve our users or whatever to make the inference. Okay, so we try to do this, and the first problem happens long before we are able to deploy anything to AWS, because actually you cannot put more than 250 megabytes into a Lambda function. And in this use case, that's really a big problem, because your libraries that you use are probably bigger in machine learning use cases. PyTorch is over half gigabyte, so it's already 2 times the size limit. If you are doing anything data scientists type, I would say, you probably won't use NumPy and Pandas, and they together are more than half of the bundle size limit. And we didn't even touch uploading the model yet, and model can be 1 gigabyte by itself or even more. So yeah, that's quite a big issue. We cannot do anything. That's the end. But no. There's a pretty simple solution. We use Docker. And if you are using Docker Lambda, like Lambda runtime with Docker, the image size limit is 10 gigabytes, so you can pretty comfortably put everything you need, all the big libraries inside it. So, okay, we can deploy something. Good. The second problem would be where to keep the model. If you did anything with machine learning models in the past, you will know that trained models tend to be quite heavy. Half gigabyte is probably the smaller model. You can have 1 gigabyte to 3 gigabytes of binary file that you need to somehow provide to the Lambda. But we have few solutions that we can apply here. Firstly, you can include it into the Docker image. As we discussed, 10 gigabytes. Okay, 1 gigabyte probably will be machine learning libraries, but we have 9 gigabytes space left to put our model. That's good. Other option, store it on S3 and download at the beginning of using, like in the beginning of your Lambda function. And in Lambda, you can use the ephemeral storage of 10 gigabytes. So again, you can download from S3 and save in the Lambda quite big files. Which solutions to use? Basically depends on your workflow. Smaller models are fit nicely into the Docker, especially if those are publicly available models that you can download from the internet during the build process. And you are doing this only once if you are making your Docker layers correctly. However, if your data scientists work like a little bit separately and they did the model, maybe it's easier for them to upload the model into S3 and then for your Lambda to download it. What is not a good option that I tried in the past, but it didn't work very well, is the EFS. EFS is the elastic file storage on AWS that you can attach to your Lambda. So my idea was, okay, let's have this EFS. We'll put the model there. It will be attached to the Lambda, so there is no need to download anything from the S3, so it will be faster. But the added complexity of setting the VPC, the networking, accessing, like uploading the model to EFS through the EC2 instance, So the virtual machine added so much complexity that it was completely not worth it. Okay, so we have our Lambda, we have our model in the Lambda downloaded or bundled together in the Docker image, and we want to use it. Great. We are trying to like invoking our Lambda, and what we see, we see that it takes forever for our Lambda to return a response, and that's problematic because machine learning inference is computation heavy, and we cannot directly increase the computation power for our Lambda function. But if you knew a little bit about Lambda functions, it turns out you can increase memory, and if you increase memory, you are also indirectly increasing the CPU power. Of course, that costs more for your Lambda to be invoked, but you can basically test and measure what size of memory will be best in terms of speed, so latency versus costs. There are tools to do that. The slides will be available later, and there's a link to the blog post about how you can measure what's the best memory for your Lambda to be quick and cheap at the same time. Okay, so we can put more memory, up to 10 gigabytes. That will give more CPU power, so our Lambda function will run quicker. Great. But we still get very big latency, not on every request now, but on the first request. And that's called cold starts. And if you are doing serverless or you know about serverless, cold starts are things that you just have to live with in serverless, and you can mitigate in a few ways. The problem with machine learning specifically here is that loading model into memory, so you have your model, you have your PyTorch library, let's say, and loading this, using PyTorch to load this whole model into memory, which needs to happen first before you can do inference, is very, very long process. And by very, very long in computer science, I mean few seconds and more. In very drastic cases, it can take up to a minute. So what can you do with this cold start when you are first invoking your Lambda function? Well, you have two options basically. One would be to use provisioned concurrency with your Lambda function. So basically you say, okay, I want this Lambda function to have 1 or 2 or how many runtimes always available, ready, warm up for me. So during the deployment, AWS will do all the initial steps with your Lambda function to keep it warm, to load, and during this time it will load your model into memory and will keep you few runtimes ready so you can use it right away without cold starts. Of course, it costs money, and if you are using provisioned concurrency, because this is then like 24/7 kept for you, you are paying the like flat price over the month to keep it warm, basically. But you have the other solution. You can just ignore it, and that's great solution actually, because turns out not always you need your Lambda function to finish in under 1 second. Sometimes waiting even 15 seconds for it to finish is completely okay, and this is the case for asynchronous inference. So the use case with, for example, images uploaded, and we are detecting what's on the image. No one will cry if in 1% of invocations this Lambda will take 15 or 20 or 30 even seconds to detect what's on the image. Okay, and keeping with cold starts, we can have another problem. We can have frequent cold starts, and that's problematic because if you have one cold start, sometimes, like I said, less than 1% of the invocations, that's okay. But with specific types of workloads, you can have a lot of cold starts. Cold starts basically start when cold starts happen when you AWS needs to create new runtime for you. And AWS needs to create new runtime for you in 3 cases. First is when you upload your function for the first time or update the function. So it's purely new, so you need to provision it, you need to do all the steps, so that's cold start. Second case where cold starts happen is if you didn't use your Lambda for some time, around 15 minutes, then AWS will basically garbage collect your Lambda function, your whole runtime. So then if you invoke it again next day or after 2 hours, whatever, you get cold start again. But the third use case, which is important for this use case, is if you are invoking concurrently Lambda multiple times. So for example, if you have batch of items, so let's imagine that we have process that will upload those images to the bucket every day at noon or whatever time. So then instead of having the workload spread over whole day, you are uploading all the images at once to the bucket, and then you want to invoke your Lambda function 1,000 times at the same time concurrently. And what you get is basically this picture. So basically, oh great. Can we not? Okay, perfect. So what we get is this picture where you have your Lambda function invoked multiple times because we have long cold starts, as we discussed with machine learning. You are waiting for the first invocation to finish, and you are invoking for the next job, and so on and so on. What can you do? Or why even bother? Why bother is because of money, because you are paying for this time, and usually the cold starts are not so long to be a problem. But with machine learning, those cold starts are basically like the time of the cold start is majority of the time of the working time. So what you can do, and that's working only for the asynchronous inference, I would say, you can limit the maximum number of runtimes that AWS will create for you. So then all those requests are put in a queue, basically, and processed one by one. But there is this the problem that those requests will wait in the queue. So that's not great for user-facing, for the synchronous inference. But if you are doing asynchronous inference where we can just wait for the Lambda to be warmed up, to be bootstrapped, to process next request, that's pretty okay. Okay. Let me show you this in practice. We have a few more minutes. Okay. So what I did is working here. Okay, so what I did was take the ready model. Like I said, I'm not data scientist myself. I took a ready model from the Hugging Face, and you can see the model. It's a binary file that has basically 1 gigabyte of size. So that's a pretty big file. And what we'll do, I will upload a photo first and then talk about other things. Because we'll have the cold start I mentioned. So let's say we are uploading this photo to our bucket. Working. Didn't log out me yet. Great. Okay, so we are uploading this photo, and let's wait a minute and let's discuss what we have here. So I totally remember to increase the font size. Okay. Okay, that's more or less okay. What we have is a very simple CDK stack, so the infrastructure for AWS, where we have three things. We have a Dynamo table, where we will keep the results. We have a Lambda function with our Docker image that has 10 gigabytes of memory and this reserved concurrency for one to process, to keep like one runtime only. And we have the images bucket that you saw a second ago, where I uploaded the picture. And in the code, great. On the code side, code is very simple. We start with loading the model into memory. And we do this like in the global scope, let's say, because this needs to happen before we handle first event. So what we do here, we basically, I copied this code from the README in the Hugging Face because I'm not data scientist, but I can copy paste code and make it work. Like we all, I guess. So what we do here, we are basically loading this 1 gigabyte model into memory, and only then we have our handler method, which is invoked with our info about new image in the bucket. And what we do here is we load this image from the S3 bucket, and we use this machine learning library, these transformers, to extract the features and generate the description of this image. Yeah, so basically the whole machine learning is those 3 lines, I guess. And at the end, when we have the description for the image, we persist this into the DynamoDB. Okay. So what happened? I uploaded the photo into the S3 bucket. Okay. And that hopefully triggered a Lambda function. And we can see how this Lambda function, how it went, because we have the trace in something called X-ray in AWS. So we can see what was invoked. So our Lambda function was invoked, and it invoked the S3 bucket to pull the image from that, and then it invoked the DynamoDB to save the description. But what's more interesting here is how long the next steps of this process of this Lambda took. So the Lambda in total took 22 seconds, which is quite long. But we can see that initialization of the Lambda took 9 seconds. And we can see that it started at 11. So with this cold start, 10 seconds took for the AWS to provision our Lambda, and then next 9 seconds took for our Lambda to warm up, to initialize this model into memory, and so on. And if you do this few times on the cold starts, this time will differ from like 10 seconds to 30 seconds. That's quite random with loading such model to the memory. And only then our handler was invoked, and you can see the handler took 2 seconds and some small part. So the inference itself was not very long. Still, the inference took 2 seconds, 0.2 basically, and our calls to S3 and call to DynamoDB took like 30 milliseconds. So we can see that firstly we have the very long cold start, almost 20 seconds, so almost the whole time was the whole cold start, and inference took 2 seconds. So if we look into DynamoDB right now, what we'll see, okay, we have this record, and we have pretty good caption, I think, if we look at the image. Okay, little girl standing on the side of the road holding a camera. Okay, pretty good. I took this model from the internet. It works. What will happen if we upload more images right now? So let's upload 2 more images. Okay. And if we go to Dynamo table and refresh it, we already see 2 more items added. And if we look at the traces of those 2 invocations, we will see that now the whole invocation took altogether under 2 seconds. So there was no initialization. The only thing that took some measurable amount of time basically was the machine learning inference that took under 2 seconds. And probably for the other trace it will be very, very similar. Yeah. So if we have our function warmed up, it takes under 2 seconds to use this machine learning model to produce the result. Okay. Could things be better? Yes, they could. One of the frequent requests to AWS is GPU support for the Lambda, because I'm not the only crazy person that does machine learning with Lambda. There are more like me, and GPU support would really speed up things. The other thing is to remove altogether this long initialization. Both downloading this, like building the Lambda runtime and loading this model into memory. And my hope is with the Lambda snap start, the thing that you may heard is like half year ago, AWS released for Java runtimes on Lambda, that basically when you deploy your Lambda, it will run this initialization, this thing, like everything outside the handler basically, and it will then store the memory dump. And then on your next invocations, you won't have cold start because you are just taking the already initialized memory dump, basically. So if we have this for Python, or more specifically for the Docker, we could get rid probably of the whole initialization 20 seconds long phase. 3 minutes left, great. Who should build it? My opinion is we should speak with data scientists sometimes, and we should collaborate, especially if we are doing anything that involves a model. So if we are building our model ourselves, our solution on Lambda, or if you are using AWS services that require training the model, like Personalize, it's good to have at least one data scientist around to for them to firstly take a look at the data that we are feeding our model, because there is this garbage in, garbage out rule with machine learning, and that's pretty good rule. And there are some fine tunings that you can do on some models, even those for on AWS, like the Personalize and so on. Some hyperparameters to set up. I don't even know what it is. Some metrics to understand how well this model is behaving and so on. So cross-functional teams with data scientists are not a bad thing. But of course, if you are using some AWS service like recognition where there is no training model at all, basically you don't need anyone else to figure out anything. You just use it. So, like summary, serverless is here to simplify operations, and you can apply this to some ML solutions. Not all of them, I am aware of it. My first place to go is AI services that AWS offers, because that's simple and we are not spending time building models because someone took care about it already. But if you need custom model, you can sometimes do it with Lambda, so why not try it? And of course it will be easier for this asynchronous option, but it's also possible for synchronous. So the recipe in short is use Docker runtime, a lot of memory, and they care about concurrency, like think about it and think about setting those reserve concurrency and provision concurrency parameters. Yeah, so and solutions like this work on production for pretty big companies, I could tell. So, thank you. The blog post with the example that I showed you on AWS is linked, and this presentation is also available on, under this code. Thank you, and I ran completely out of time, but I'm happy to discuss serverless or machine learning with serverless with anyone, maybe outside. Thank you.